In this problem number 2 for Kinematics 1, we're considering a person who's at a particular latitude. And how fast are they moving through space if they're at that latitude? Well, let's just think what's going on. The Earth is spinning on its axis. It spins around once a day. To figure out how fast they're going, we need to know how far they went and how much time. Well, 24 hours are in a day. So really the hardest part of this is figuring out how far they would have went. If they're at an angle theta of latitude, how far did they go in a day? Well, let's take into consideration this diagram of the Earth. So draw a little diagram of the Earth here. And we're going to represent the Earth as a sphere. I know that doesn't look exactly like a sphere, but we're going to say that this is the equator. And at the equator, there's a very known value for the radius at the equator. So let's go ahead and just draw in a radius from the equator. And let's label that with R, capital R being the radius of the Earth. And then let's consider let's actually go back to this color. Let's consider this latitude. It's defined by the angle of the latitude. Let's say that's theta. Well, at that latitude, we have this circular path that a person on the surface of the Earth would be traveling around. And that circular path, of course, has its own radius. And let's call that radius. And let's just label that in here. Let's call that radius little r, or lowercase r. And just to make the geometry a little more clear, I'm going to draw in a vertical line here, or a line along the axis of the Earth, which would be perpendicular, or you can draw a perpendicular here because you can construct a right triangle with these radii if you choose the right ones. And we have basically this capital R is also the length of this hypotenuse. And theta is also this angle because we have parallel lines. If we choose the radius up here and the radius up here to be in the same plane, then these lines will be parallel, where you have an adjacent side and a hypotenuse of a right triangle, and this angle theta defining our geometry. And from there, you can determine that the little r is given by the big R, or the radius of the Earth, times the cosine of theta. Now, the big R, the radius of the Earth, is only really good in a spherical approximation to two significant figures. We can say it's about 4,000 miles, but more precisely, it's better to say 4.0 times 10 to the third miles, which is going to limit the precision in our answer. I hope this helps you in Kinematics 1, problem number 2.